Oh,
You want me to open this?
And then I've got the code on my phone.
Right.
can you also log in from here? Yeah.
So then, meet, I think meets at google.com. Then when you go there, it'll prompt you for a code, I think.
Use a meeting code.
Yeah. So it's, perfect.
So I'm not using camera. I'm not using sound. I will join meeting.
You can. Oh yeah, go ahead.
And present to me there.
You have to.
Oh,
ask
so
him
we
to-
have to back to this computer. I think we'll allow it. And then,
Yeah. Can we wait for him to join?
well, I just let him join.
Yep.
So there you go. And then
Share.
if I, you're present.
Yeah. Just hang on 1 second. Okay, I think we're good.
How we can tell if people see it? Oh, it's my screen, obviously.
screen, yeah.
Duh.
Does it say shared somewhere?
Hmm?
Does it say shared somewhere on your computer?
Yeah,
Stop
yeah,
sharing.
down
Yeah,
below.
we are good. You
Can
can
I-
blow
can
it
I-
up now.
Yeah, I can put this in the regular place where I know where is it. Like the WebEx and others, they put this on top, so I'll put it here. So I remember that I'm sharing stuff.
We are ready to get started. So folks,
Do it.
ready? My name is Vinay Narayana. I work at Wayfair. I'll go later when I'll do my introduction, but we'll kick it off right now. So thanks for coming this evening to spend some time with us. We're very excited, happy.
We have a few seats over here as well, so if you wanna, people who stand in the hallway, they can sit here. There's plenty of room here. Just a suggestion. I don't know. Yeah. If you don't want, you don't have to. But we strongly encourage.
I hope everybody can hear me if you don't. Right, louder. Louder? I'm gonna use the mic.
I think we have this one. Uh-huh.
Is this better? Okay, great, awesome. So we'll kick it off right now. Viktor is gonna review his presentation, as you can see on the slide here. Just for logistics, many of you have already seen the food. There are drinks. If you want to use the restrooms, you have to go through those double doors right behind this room and make a left. Both the men's room and the women's room are right there. If you are looking for a trash can, it's on your left. You go out, make a right. I did say that there was beer. I lied. Unfortunately, all the beer in our kegs is gone. We do drink a lot of beer around here in Wayfair.
Just Tuesday and the beer is gone. What the hell is going on? It's a fun place to work. Are you guys hiring? Like beer is right now on Tuesday because people coming Monday and drink all
Yeah,
beer.
pretty much. All right, without further ado, I'll let Viktor get started on his presentation. Since we are recording, if anybody wants to ask a question, just raise your hand and I'll run with this mic to you.
Alan, you want to just briefly introduce yourself?
So my name is Alan Warner. I work for Confluent. Can everyone hear me?
Yeah.
I work in a non-technical capacity, so I won't speak very much. We'll leave that to Viktor. But I do work in our Boston office. We actually just opened a satellite office, and we're going to expand into what I would like to call a Northeast hub for Confluent. So if anybody has Confluent-related questions that are non-technical, you can come see me or one of my colleagues here. For technical questions, you can go right to the red pants in the front.
The Confluent people wave a hand so people would know you. Awesome.
Yes, very good. So also I will say there is a raffle. It's my last warning. We're going to do 2 drawings, one in the middle in between the sessions and one at the end. But there is a Kafka definitive guide, which is a really important book if you're looking to learn more about Kafka, and some other goodies there. So yeah.
All right, thank you. Yeah, I probably also work not technical capacity. I'm a part of the team called DevRel. We actually, no, I think it's somehow technical capacity because we also talking to engineering. So hello, my name is Viktor, and today we're going to be talking about Kafka. How many people came here to talk about Kafka or listen things about Kafka? I think it's our first meetup, right, in Boston about Kafka and stuff. So like people excited. Are you guys excited? Yeah. Amazing. All right. So Mr. Kafka is excited. That's a very rare photo of him smiling. So yes, I work as a developer advocate, meaning that I'm here to talk to you. You know, if you want to talk to me, just grab me. I can talk as much as I want. I also have a raffle, but I'm striving for attention. So that's why go follow me on Twitter. Take a pictures, send this in Twitter. Tag me in Twitter, and also share it with hashtag Boston Kafka. Let's make it trending. And if you will, at some point, will forget things, they conveniently are placed down below. So every slide you can also add. This is a Confluent account, so you can also go there and check this out. So today we're going to be talking about Kafka. Why is Kafka, and what's this thing, event streaming platform, what all this about? And I want to start with inspirational, some of the inspirational, not the quote even, but some idea that how the Kafka came into place, where it came from, and how the people came to the realization that, you know, this is the thing. And essentially, companies, like when we're talking to people, the company built on top of like data flows, right? Information is flowing across the company, across different departments, So I think this is the speaker here, so I'll try to not go there because it will be. I need to wear it, right? I need to wear it because I can be a bit louder, but without wearing the mic. Anyway, so, but we're building actually like applications that just, you know, hides the data. So basically what we do when we build some of the enterprise information system or information, whatever application, we build an application. Application has some business logic, there's some storage, database, some of the application expose APIs, some APIs will be used different applications, and so far and so on. There's some faster application that provides request response type of paradigm, and they send, it's nice, I'll send here. And they have a request response paradigm, so that's why the latency, how this application are working, this would be much lower. Some applications we're using like data warehouses or maybe some Hadoop clusters, they have a higher latency because you don't need to have immediate response, right? And so far and so on, so many, we're building public cloud, private cloud, everything goes into this different applications, many applications. Now you start talking to applications, and this is how you basically have a job security. Because if you know all this stuff and you would be only one person in the company who knows this stuff, you will be here for a very, very long time, right? So I'm here to kind of change this. So this is the idea that came into play from back in the day on LinkedIn. They would have multiple different applications, and these applications were interconnected to each other. And there was like almost like impossible to figure out where's everything and like how is everything is connected. There's Kafka. Kafka is over here. Kafka depends on Zookeeper. There's Hadoop. There's Hive. There's Peak. There's Storm. And this is like your enterprise architect. So essentially, the streaming platform is a tool, is a set of tools that allows to change the way how we're dealing with data exchange or how we exchange the data inside the organization. Streaming platform kind of tends to be a central neural system of your organization, of your informational part of your organization, right? And we're changing the ways how we're dealing with data through, you know, integrating slow systems, like they naturally slow systems, because Hadoop and different data warehouse systems, they're supposed to be slow, but not because they slow, but just simply because they're doing the way how they're doing the batches. There's a lot of information, stuff like that. We're breaking down monoliths. So monoliths, even though like we have many professionals in the room and the people know how to build highly modularized application, but still it's a monolith. It's a piece of one big application. We want to go to microservice architecture because some people don't necessarily need to write the same application in the same language, for example. They want to write in different languages. They just want to have a data exchange, right? We're switching from the batch because batch is bad, batch is slow, but not allows you to get the result immediately. We're switching to real time, right? This is essentially how everything starts. You know, everything starts with the million of messages. These messages come in real time. They hit your high throughput system, aka Kafka. We perform some continuous computations. In this case, it's a part of the Apache Kafka streams. And it's a Java framework, and KSQL that allows you to do processing data as it comes. And after that, it can be served through the REST endpoints. It can be dumped to Elasticsearch for full text search, so far and so on. Essentially, I want to share 3 things today with you. So one thing is 3 essential features for streaming platform, and I hope these things will give you idea how this stream platform is different from other type of software that you were dealing before, right? So we will talk about storage. We'll talk about the pattern, the pop-up pattern, how it fits here. And we talk a little bit about the processing, how to do data processing on the stream, obviously streaming platform, want to do stream processing, right? Storage. Now, I have a question to audience. We have a database, and the core abstraction in the database is a table, right? Everyone agree? We have Hadoop, and Hadoop was based out of the distributed file system, a GFS, and the file was core abstraction. What is the core abstraction for Kafka? Like, what's the similar thing that everything is based on? It's a log. It's a commit log. So basically, you writing your application, and you want to capture all the events. You writing this into log. How many of you Java developers here? Log4j, SLF4j, Log4j2? Ooh, это .NET? .NET, okay. Still a log-based application. You're writing something into a file, always appending your file, right? You're not changing log unless you're trying to cover up some like crime. You're not going to logs and changing those. So remember, have this mental model during this presentation because you will understand many things. And same mental model that we have in .NET and Java and many other languages is that log is actually sequence of immutable events or records or whatever, but immutability is a part. So since you cannot change like words that you said to your significant other, only thing that you can do is to send your sincere apologies, right? So you can send another event to either amend, but it would be dependent on how the receiver will receive this message. You know, there would be some latencies on consumption of the messages because the previous message was more higher impact, so you need more time to process it. Now, the log is actually a very simple idea, right? So we already talked about this. So you're always writing to file, and you're reading from sequentially, you're writing sequentially, pretty much it. So that's it. But, there's 2 most important data structures in the data engineering. Log, who can tell what's the second one? No. What questions, if you travel somewhere and you're getting back to States, what question the customer control person can ask you if you answer your programmer? It will ask you, do you know what's the B tree? Binary tree, B tree. Also B tree used in databases to build indexes. It's important. It's important. Two data structures that you need to definitely know. Also, if you didn't know, log is actually also used in database designs. Everything, when you do your insert something in your database, it actually goes first in transaction log. And after that, the database management system materializes it into table to view or whatever representation of this data. Okay? So we're writing these messages. Messages are keyed. There's a key, there's value for a message. And there's also an index. There's offset, so you know where this message came from. Basically, it's a monotonically increased number. It's always growing. This is pretty much it. From perspective of storage, it's a distributed event log. You're putting data into the end of the file always, and your message is never gonna disappear. You can have an infinite retention. You can store this data forever. Like again, some of the messages that you send to significant other, she can remember this forever if it was good or bad or whatnot. So it's up to you. It's basically like how long you want to keep this. It doesn't matter. All right. This was dramatic. Thank you so much. You good? You're not heard? So next thing. Okay. So we talk about storage. It's nothing to talk about storage now. So pops up. So since we're writing data to file and read data into file, we need to have two components that read data to file and write data to file. So the simple, we start with the writing data. And as we learn, over the time, we're writing to the end of the file and we're constantly growing our file. And this is how you put this message. And on the other side, you have a consumer that can read the message. And interesting part of Kafka system is that or like the first time when the people start using Kafka, they start thinking, okay, so how it's like I consume the message, but message still in Kafka. So this was an important thing in my previous slide when I was talking about offsets. You actually reading and you actually writing only committing offsets. You're saying, okay, so I'm done with this message, I'm going to the next one. And message never expire. Like I said, you can always return and relive these memories, right? So, for example, my birthday was in April and it's coming in April, but my birthday is year before. I can remember all these events, right? I can remember this, and different people who also were invited or not invited to my birthday, they also can remember this event or don't remember this event. So they still have a same kind of shared history, so they can read this message, but they remember different things. They might remember different events, different things that happened during this. So that's why these consumers, different consumers, they can relive this or remember this event or read this event or process this event on its own pace or its own speed, so far and so on. And the message will not disappear after consumption. This is a huge difference between traditional messaging systems. So next. So Kafka has actually more properties of a distributed database than messaging system. Because Kafka provides you horizontal scalability, you can put your data, your distributed log into distributed form that will form topic, that data structure that your producer and consumer work. And it's kind of interesting why it was called topic, probably because of mentality of the messaging is very deep in our brain. So we're still trying to find like similar words to describe a little bit different thing, because it doesn't fit into like table as well. So essentially, how you write this? How many of you heard about consistent hashing? Consistent hashing, for those of you who don't know, it's idea how you write data and how your the server and client agrees upon where the data will be placed without involving like third party. Like you don't have a discovery server if you don't know where the data on which node holds this data. So this is why I'm using this simple algorithm. Take a key, apply the hash to this key, and have a mod on
number of partitions. So that's why you're getting the node where this message will be stored. So when you have a key in your message, when you're producing something into Kafka with key, message will be placed into a particular partition. This opens up very interesting property that Kafka is also known of, is guaranteed order within partition. Since you will be using message with the same key, or at least message that can produce same result, they will be placed on the same partition. And how this message was produced, this order will be preserved on the other side. So your consumer can read this data on the same order how this message was produced. So I'll give you an idea, because every time when I talk about money, people take like paying attention, or I'm talking about credit cards and stuff. So you have a credit card processing stuff done in Kafka, and you want to have your credit card number as your key. In this case, all transactions that happened with this credit card, they will be placed in the order how they actually happen. You don't want to have withdraw after deposit or whatnot. Maybe you want, but you want to have order of these operations. So the having this key and having message with the same key will guarantee you this order. Any idea how we can do global order? Huh? No. Okay. Yes, we have a. Can we throw some prizes there, because Alan is our responsible for prizes. Can we throw prizes to people? Give people prizes, because yeah. Yeah, that's a good question. So yeah, you can get the pen. Yes. So if you want to have a global order of messages, you just have a topic with one partition. Your performance would be terribly slow, because you will not be able to use all this high scalability, high throughput platform, because everything will go to one partition, to one topic. But hey, you want to have a global order, you need to have some sort of trade-offs. If you're not specifying, so if you're not specifying key, your message would be placed on the run robin fashion. So that's it. That's easy. Two models how you publish things. If you're not specifying a key, it will end up somewhere. Now, consumers on the other side can, as I already mentioned, they can read on their own speed. We do have a fast reader and two slow readers, my colleagues. They're actually better on reading, because they're better on everything. I just want to show off here. But essentially, they move through the same log, and they operating on the same data. They might have different algorithms to produce. For example, I'll give you an example from life. We're reading one book. Together we have a book club, but we're reading one book. It's weird, I know. We're reading one book. It's physically one book. And the way how we can figure out where we stand, we have using different bookmarks. So basically, when we put the bookmark on the page, this is how we commit our set. This is where we know where we stopped. So basically, since English is a second language for me, I'm reading much more slower than people who, this is like English guy. English is super best. So this is why how we're reading this book. We're reading this book and we're putting these bookmarks. So, and at some point, the way how I process these words requires me to go and look up some words in vocabulary. So in this case, I do enrichment of the stream. So I'm consuming the stream, and the result that I'm producing as a consumer is enriched stream, because I also getting definitions of certain words, right, on the process. This is why my processing might be slower. Or if my processing is just, I'm just going there and reading. This is what example here. I'm just going there and counting words. I'm not reading book. I'm just going there and counting words. So that's why it's faster. So it really depends what kind of data processing functions are you guys using, right? So, but again, messages will not disappear after you read this. They can disappear after a certain time. There is a processing called retention. After a certain retention period, the messages will be automatically evaluated by Kafka. So you don't need to do anything except configuring the particular topic. This is how we go. All right, makes sense? Does make sense to anyone? All right, cool. So, Victor, you said this is a key. Can we read by key? Can we do random reads? Yes, you can, but you should not. Kafka is only supposed to be used for sequential reads and writes. Kafka is not distributed hash. Kafka is not distributed cache. It's not distributed in-memory data grid. It's not distributed database. All this speed that you're reading in blogs and internet, how Kafka can process the millions of messages, trillions of messages, whatnot, sequentially, right? If you want to have a random access, you need to offload this data from Kafka somewhere, some system that allows you to do random reads and writes and whatnot, right? But not in Kafka. Okay, this is a very important slide. It explains everything that you need to know about consumers and consumer groups. So you have a consumer group coordinator, which is the part of the broker that will be responsible for reading consumer with partitions. We have topics with n number of partitions, and our consumers, they grouped in the consumer group. This is another property of Kafka that doesn't exist on the messaging systems. So if you want to scale your reads, aka you want to eat more worms from mommy bird, you can have more consumers, more baby birds that can eat all this worm. Okay, if you, for some reasons, maybe one of these beautiful birds will fall out of the nest, it's okay, because there's still plenty of food, and other consumers can share this food. So the mommy bird will stop the process of feeding. It will redistribute a partition across all these consumers, and they continue to consume. So here's the interesting thing with the consumer groups and the number of partitions. You cannot have, only actually you can have, but you shouldn't have more consumers in consumer group more than your number of your partition and topic. Simply because what happens if mommy bird doesn't have enough worms? One of the baby birds will starve. So is your consumer. So consumer is always kind of like a one to many. One consumer can consume multiple partitions, but there's always will be one consumer per partition. You cannot have two consumers per partition, because in this case, it will break guarantees on ordering. All right. Now you have it. You saw it. You will probably will never forget this. Yeah, but like for enterprise architects picture. Now, this is one consumer that reads all partitions from the topics. Multiple consumer groups that read multiple topics. So this consumer group 1, consumer group 2, they consist on 3, maybe 4. 1, 2, 3, 4, and 4 here. 3 consumers. Because 4th partition, obviously. Right. So when it goes into a consumer group, one of the consumer will go down, one of the partitions will be available on another consumer. So this is it. This is what your streaming platform looks like. So this is the first step of your streaming platform, probably the most important one, because it's responsible for storing the data, for horizontal scalability of the data, replication, which is also important, because sometimes you also can, one of the machines can go down. So how you can provide a resiliency? Usually, we're using replication to do that. So we have one machine that will hold leader replica of your data, and we have a replica that will be stored on another machine. Also, the picture for enterprise architects. So you have a topic that actually spread across multiple partitions. Topic 1, topic 2, topic 3, and topic 4. But also we have for example, partition 1 replica stored in the broker 3. And we have topic 1 partition 3 stored on the broker 1. So if one of the nodes will go down, the process will rebalance the cluster, and one of the replicas will take a leadership of certain partitions. So as you can see, some of the things we still have our data because we have enough brokers. So we lost, for example, this is the leader for topic 1 partition 4, and now the replica that was stored on broker 2 took over responsibility for a broker, for a leader. Now, probably most important slide, because I will definitely get any questions how it's different from ActiveMQ and RabbitMQ. So in 3 words, much better scalability. When the Kafka was designed, it was designed by people who were building databases, because Jacobs was building a, what's the name of the coffee or something coffee database, document-oriented database in LinkedIn, and Voldemort is also was database. So horizontal scalability is the thing. It was based, design of the Kafka was built on this one. So some of the messaging systems, they add this horizontal scalability capabilities afterwards because people start needing it. Kafka has it out of the box. So full tolerance and high availability. So replication of the sum of the data is already built in. So it's available for free and it's configuration-wise. Plus, usually in the messaging system, if you want to have durable messages, you need to somehow attach them to databases or some other provide some limited durability of your messages. Kafka is, think about the Kafka as, if you like to think about Kafka this way, as a messaging system with database durability guarantees. So how many of you guys and ladies heard about Jepson? We have some distributed systems buffs as myself. So basically, there's a guy in the internet. He's just going and writing tests for different databases and trying to prove the claims of different vendors. If they telling people, okay, so my database is globally scalable, highly available, and so far and so on, he breaks them. And he has this like a set of tests called Jepson. It's really interesting reading if you're into distributed systems world. He explains how he builds this like correct, how he tests the correctness of basically of consistency of distributed systems and how they perform under certain weird conditions. And there's a test for Kafka, and Kafka has very good points in his scale. So which is pretty cool, meaning that you can go and try to replicate the same test if you know how to read and write in Clojure. Anyone? Clojure? Yeah. Okay. Obviously. All right. Enough talking. So I wrote a small app that show you some of these concepts. Here I will be using the Confluent distribution that we called Confluent platform. So it actually has multiple interesting things that I didn't talk about today, but still. It will scroll up quickly. So I'm just starting right now everything from the very beginning. So we have a Zookeeper. Kafka depends on Zookeeper. Zookeeper, it's the also kind of sort of distributed database that stores some of the metadata for Kafka. Obviously, Kafka, we need to have Kafka to do our things. Schema registry. Schema registry, it's a cool component that allows us to store metadata about our data, aka schema. REST proxy allows to produce and consume data from Kafka or to Kafka just from curl or bash or from browser, right? That's cool. Kafka Connect allows to ingest and ingest data just from any possible system. There's plenty of connectors available in internet. KSQL Server, we will talk about KSQL a little bit afterwards. And the Control Center, which is basically the UI that we use to monitor Kafka. Now, my application is actually, oops, let me kill it. My application is, I think it's pretty cool. So this application actually, it's called K-Lift, because Kafka and Lift. So basically, you have a driver, you have a writer, and the app that driver uses will be on the one screen, and the app that the writer uses is available on another screen. So when the writer wants to go somewhere, he just place where driver needs to come to pick it up, and the driver comes to pick it up. So it's so I will open these two screens. So I will use tune. By the way, this app is available on GitHub. It's my GitHub. You can go there and grab it and play around this. If you don't mind a little bit of any Scala fans here? All right, sorry guys. Yeah. Because just, I don't like Scala. I cannot do Scala because I'm too dumb. So Kotlin is better Java. It's fine with me. So two pieces. Now, first one is a driver. And instead of just doing like the simple hello world to write to topic, read from topic, I decided to just show you this one. It's, you can go there and check this out. It's like Spring Boot application. It's cool, right? Spring Boot fans? Okay, even less than Scala people. What's the framework folks using for writing microservices? Grails? Go? Ooh. Again, I'm too dumb for things like Go and Scala. Probably Go would be something interesting. I can learn Go. So let's see if it's while I'm talking, my app is loading. Hopefully, let me see if it's me or something cached. If it's actually working internet. So it uses the Mapbox service to draw the maps, and let's see, it's actually downloading something. So it works. It goes to my WebSocket. Looks like it's loading something. All right. I'll give a second. Trust me, I tested right before this. It worked. Worked on my machine. Happens every time, right? How many of you said this today? All right. So as you can see, our driver starts from a place where we are right now, and our writer, loading, wants to go somewhere. Where do you want to go, Fred?
Museum of Fine Art.
Can you show me on the map?
So it's this way.
Okay.
Where are we? It's somewhere right about here.
Here. Here. Oh, yep. Okay.
Yeah,
So, okay. Boom. Yep. Okay. I'm in the Museum of Fine Arts. So my driver actually sees me and say, "Hey, boy, I'm coming." And I have my and the guys actually start moving, and the car is actually moving with the real time thing. So it gets the information about roads from Mapbox. The cool thing is that this guy is also can see how the driver fastly moved to it. Yeah, maybe it's a flying car. Maybe we'll go directly through. What do you want? It's demo. So the cool thing about this, the cool technology behind this is really cool. So yeah, we have a Kafka, and I use actually two topics. One topic is information that the driver publishes, and the writer is actually reading, and vice versa. So the writer also can publish information. The moment when I said, okay, I'm here, information was published into the writer. So let's see if we can see any data. Ooh, no cluster. Let me refresh the screen because never happened before, but and here we are again. So driver goes inspects, and we should see some messages that the driver sends coordinates through Kafka topic, right? So there's some information in the driver ID, so we know that we're actually doing some. This is our driver ID, this is our rider ID, some UID, and some information about the driver position. What's the status of the driver? The driver is going to pick up our rider from the. Let's call him Fred, because he wants to pick up someone from Museum of Fine Art. Now, apart from that, so you can also consume this from the UI, and I do say writer. And the cool thing about Kafka is that I can also, because I want to see all messages from writer, but I was not there when the messages were published. So I want to go from beginning. So in this case, I will see how I can do that. And there's a flag that allows me to, let's do bigger. As far as I understand, it's something from beginning, obviously. I'll do writer, and I'll do from beginning. So in this case, even though my writer already consumed, or my driver consumed message from the driver when the moment that was picked up, I still can reread this message and can perform something else. For example, like with the messaging system, you can do some of the real-time bits. You can say, yeah, that's easy. But with the event streaming platform, you actually can enrich this stream, include some additional information, or like the check, like if he's on in the place of the city where it's safe, things like that. So we can also send contextual notification to the user. So now nothing is going on. But if we do driver, so in this case, we also will do from the very beginning full information. And now it's still continue to, because writer doesn't send much of information, it just waits. And the driver sends constantly this information that where driver is. All right. So now quickly about the processing, because I cannot, technically I can't like speak about this like whole night. I have plenty of material to talk about this, but my goal today is give you overview and get you excited about this thing, so we can ask, can Viktor come back? And Viktor come back, because I'm not far, I'm in New York. So and the processing. So processing. So basically, stream processing, this is a procedure or toolkit that allows you to process data as data arrive, obviously. We have multiple streams. We can join the streams. We can produce something as a result. And when we're dealing with Kafka and the Kafka streams and the KSQL and some of the tools that kind of built in Kafka streams, we're usually talking about the stateful stream processing. Sometimes, like to get the result of in this particular moment of time, we need to have some data from the past. For example, we do running overage, we do sum, we do count. We need to have result from the past. So Kafka streams, KSQL, they're tools for stateful stream processing. Now, again, to get your attention, I will be talking about money. So every time I'll be talking about money, possible fraud, credit card transactions, all this stuff. You should know that this is where you need to pay attention. Now, how we can check like all of authorization attempt is fraudulent. So this is basically demonstration how we can get a stream of credit card transaction or like credit count authorization attempts, and we're trying to figure out is it possible fraud. So we have a very sophisticated algorithm about this. If our authorization attempts happen more than 3 times in the last 5 minutes, so we would say this is our possible fraud. So we have this is what we call like KSQL, which is streaming SQL for Kafka. And apart from the thing, probably window thing, it looks like a regular SQL, right? Except again, stream probably. But let's break it down. So first of all, we're creating another stream. We derive one stream from another. So that's why we're creating a stream from possible fraud from authorization attempts, where every 5 minutes we want to roll over. So this is where we will be dealing with the state. So because we don't really care what happened, like if it happened 3 authorization attempts in 1 hour, probably it's okay. Probably our customer is doing something fine. But when it's like it happens like very quickly, probably something is not right. We're only interested from initial stream, from the input stream, we're only interested in the credit card number. And we use here, it's the count, it's our function that will allows us to do aggregate operation. There's also obviously scalar operation that allows you to do maybe like small transformation. We have a KSQL cookbook where we can go and look all different recipes that can use all these functions, or you can even learn how to write your own functions yourself. Now, we're grouping by credit card number, so meaning that we will the count by credit card number, and the count will know what exactly to count. So this is pretty much it. This is very powerful. You don't need to write Java, Go, .NET. You don't need to write anything. This is what you go and execute, and this is going to be constantly running. This is a stream processing function that will be running inside the server, and you don't need to constantly check it. As a result, this possible fraud also will be persisted in Kafka. So in this case, you might have, let me switch. Yeah, that's very nice. In this case, you might have different application that also connected as a result, connected to result of the stream processing, and they can also perform whatever they want, right? So in this case, it's kind of you have ability using Kafka, you can fan out the data and have multiple consumers read this. You can send notification, yeah, that's possible fraud. You can send this information to dashboard and draw in how many potential fraudulent transactions happened in the last 5 minutes and things like that. Obviously, it can scale. Remember story with baby birds. This is how you scale your applications. Your applications will run as a consumer, and the number of consumer will allow you to, basically the protocol of consumers allows you to scale this. Now, all these things are standing, on the shoulders of each other. So this is low-level API that's available. It's basically you understand how the protocol works. You can write your own the producer consumer, but you shouldn't. But also you should think about this API is like your assembly language. You're using this low-level things like subscribe, send, start transactions, so far and so on. If you want to embrace more like a stream, more like a functional approach, I don't want to be asshole for Scala people. We do have API for Kafka streams in Scala. It is native, and it's actually much better than Java. The Kafka streams is actually built on top of Kafka consumer and producer. We have a KSQL that built on top of Kafka streams, so you don't need to. We wrote this in Java, so you don't have to. You're using this DSL that allows you just focus on actual data streams and performing certain operations. If you still want to write some like user-defined functions, in this case, you need to write Java, but you don't have to if you don't want to. And how to choose? There's so many choices, but essentially flexibility gives you like low-level API. Ease of use give you KSQL type of thing. I probably destroyed your raffle because I'm offering the Kafka books electronic version. Actually, the most important link is this one. How many of you know that we have this like a Confluent community Slack? All right, cool. We have a few people who know this, but essentially this is where all people in streaming world hang out. We have a Slack there. We talk about core Kafka, stream processing, Kubernetes, DevOps, whatever, or like information about meetups. It's a pretty cool place to be. And information about meetups. And before I will pass my microphone, I have one last thing. You're probably thinking, Victor, what the hell t-shirt are you wearing? Anyone? Okay, I will explain this. So what happens is actually, we didn't come up with this one. It's actually came from one of our customers. And he has to do some presentation for upper management, and his manager told him, look, Mike, I know you're excited about your Kafka project. It was a huge success. People got excited about this. And we know you're excited, but there's like C-level people. Do not oversell. They might not understand technology. Because it's fine, I'll do this. So, and he goes on the stage. And he also says, like, today I want to show you three things that changed the history of humankind. Invention of fire, invention of wheel, and invention of Kafka. And my clicker dropped. Thank you very much for your time. You know where to find me. You find me in Twitter, or you find me in Slack, community Slack. Thank you so much. And I pass the microphone to Vinay and Fred. Right. How I stop this? Oh, and our car is actually arrived. See, it's arrived.
All right.
Okay, I just use, you have a
Hello?
notation.
I don't want to butcher this. UV? YUVI? Woo! Yes. First winner. Give it up.
Oh, yeah, absolutely. I don't
If you did not register for the raffle, you can right now. We'll do another drawing at the end.
Can you guys hear me in the back? Yes. All right, great. Wow, so that was one amazing presentation from Viktor. It's going to be extremely hard for us to top what he has done. So thank you, Viktor. Great job. So we are here. So we're gonna. It's too bright here. I'm gonna stand here. Hey, Fred, would you mind doing the slides for me? I'll give you a cue. I don't know how you can hook up a clicker to this.
It also doesn't stop me. Like, where's the computer? Okay. So, yeah, sorry. I tried. I have a USB, so we can.
I think it's probably that down there. It's a Chrome OS. It's something we deployed very recently at Wayfair. Anyway, let's get started here. My name is Vinay Narayana. Hang on, I'll give you a cue. My name is Vinay Narayana. I run the big data and messaging team at Wayfair. My team consists of two parts. One is the Kafka ecosystem. My team also supports the big data ecosystem consisting of Hadoop, Spark, and Presto. For Kafka ecosystem, we have, outside of the Kafka brokers, we use Kafka meter makers, Kafka connectors, Kafka cruise control, as well as the Kafka REST proxy. So as you can see, we are pretty much bought into the Kafka ecosystem. It's pretty heavily used. And the presentation today, we're going to focus on the role of Kafka at Wayfair and the journey of Kafka at Wayfair over the last few years. As you can see in the next few slides, you'll realize how exponentially Kafka has grown at Wayfair. And by the way, I've not seen anybody ask questions, so please feel free to ask questions. So if somebody can take the mic to the person who's going to ask the question, that'd be great. Okay? So we want to keep this a little bit interactive and lively as well, if you could. So for the agenda today, we'll start off by talking about why Kafka is important for Wayfair. What is the role of Kafka? Then we'll talk about a few data streams, business use cases that make Kafka so critical for Wayfair. Some of the things I believe Viktor already touched in his presentation. Then we'll talk about how Kafka evolved at Wayfair over the years, specifically how many messages we were processing a few years ago versus how many messages we are processing now. And there'll be a trivia question at the end of that. Then that will be the easy part of the presentation, which I'm going to be doing. The tougher part will be going to Fred. Obviously, with exponential growth of Kafka, you get a lot more responsibility as well. There's so many data streams using Kafka on a daily basis. You want to keep the lights on with Kafka on an everyday basis, pretty much every second basis. Now, how do we do that? That's exactly what Fred is going to cover, how we monitor, how we keep our pulse on the Kafka health every second of the day. If you can go. As Viktor, I believe, already mentioned in his presentation, Kafka is our nervous system, is a nervous system at Wayfair. It basically connected to pretty much everything. Most of the user actions on the website, if not all, everything go through Kafka. The inventory that you see when a person clicks on an image to view a sofa or a couch or a table, all of that is recorded and all of that is processed through Kafka. right? So any action that you see on Wayfair, Wayfair.com, pretty much there is some interaction with Kafka at that point. And there are numerous use cases that we laid out here. I'm not going to go through all of them, but on the next slide, I'm going to touch upon 3 of our major use cases. First one is the scribe or clickstream. So clickstream data is basically a user going onto a website, looking at a couch, looking at a table, adding a item to their shopping cart, checking out, ordering something, checking on their shipping status, and things like that. All of the data is recorded on our website, just like any other website out there. And we keep track of what the user is doing, right? So all of this information is fed into numerous systems at Wayfair, and we use the data. We have legions of data scientists and business analysts at Wayfair, and all of these guys are actively reviewing the data and figuring out how to, gain business knowledge out of it. So some of the use cases around that is the recommendation services. How many of you have gone to Wayfair.com over here? Cool. All right, good chunk of you. So I'm sure if you have gone and seen a couch, it would say, people who have bought this couch have also bought this chair. I'm hoping you guys saw that, right? So all of that is called recommendation services. And we have a team which basically focuses on how best to recommend based on user behaviors, right? On what you click, what you see, and all that cool stuff. So this is a significant use case at Wayfair, and all of that is processed through Kafka, which is quite awesome. Wayfair has grown quite exponentially over the last few years, especially in the last 1 year. We pretty much doubled our headcount. Oh, by the way, we are hiring. So if anybody is interested, please come see me after the session. Anyway, the point is, with the growth, we have several dozens of thousands of servers that we added to our infrastructure, both on-premises as well as in the cloud. Now, we have a dedicated team, which we call Wayfair Operations Center. These guys are 24/7, and they are looking, they have a pulse on all the systems at Wayfair every second of the day. When something goes wrong in any of these systems, obviously the user experience is impacted, and which is important for us. For these guys, for them to root cause a problem, they need information about pretty much everything in one place, and that is our logging infrastructure. So they use, so we have Elasticsearch. So we have pretty much all the logs from every server out there at Wayfair pushes logs into Elasticsearch, and it's available at the click of a button, right? The beauty of Elasticsearch is you go look for an error from like a string, and it can show you across the data stream how that error has propagated. So you can quickly root cause. So it's pretty critical for our Wayfair Operations Center to use our logging infrastructure. And similarly, the metrics. Our metrics is served by Influx. We collect several thousands of metrics pretty much every second, and all of that is processed through Kafka. And lastly, but not the least, is Orwell. It's basically our internally developed SIEM platform. As part of this, it's basically every user that logs in to our website, or even an employee logging in to one of our on-premises clusters or on-premise or the cloud nodes. We track all of those logins, right? If there is a denial of service attack somewhere on our website, our SIEM application is able to figure that out. And all of these logs are going through Kafka again. So this is the slide where we talk about the evolution of Kafka. So the story or the journey of Kafka really started back in 2014 when we deployed a small cluster in our Seattle data center. At the time, it was more of a POC. And we started deploying it and working through it. It was only about 1,000 messages per second that we were seeing, right? And then fast forward to 2015, the interest in Kafka grew a little bit more at Wayfair, and then we expanded our cluster as well. We adopted what is called a local-only architecture. Fred is going to go over in a little bit more detail on what the local-only architecture is, as well as the local and aggregate architecture is in the next few slides. But for the purpose of this slide, A local architecture is basically you have one Kafka cluster where an application produces to, as well as consumes from, right? So that's the reason it's called a local architecture. So we adopted that architecture back in 2015. By the way, LinkedIn made all of this architecture popular, and we kind of followed what LinkedIn was doing with their Kafka deployments. Then moving on to 2017, the interest in Kafka grew more. We were processing about 150,000 messages per second, and we had to come up with a more sophisticated architecture for Kafka, and that is what ended up being the local aggregate model. In a local aggregate model, what happens is the applications produce into Kafka local cluster, and then they consume from the aggregate cluster. So there are two clusters, and we have mirroring between the two clusters. So the mirroring is always, mirroring data to the aggregate cluster as and when the message is produced into the local cluster. So the consumers are always consuming from the aggregate cluster. Fred is going to go into a little bit more detail about that. Last year was the turning point, if you will, for Kafka at Wayfair. And last year was when we saw a huge increase in the number of nodes and clusters we managed at Wayfair. The first half of 2018, it soon became apparent for us as we were processing lots of data, lots of messages from some of these use cases I spoke about, like the scribe data, the logging metrics data, the Orwell data. People were getting very worried that if logging would take up all the resources on the cluster, then the scribe data would suffer, or the Orwell data stream would suffer, and so on and so forth. So it was important for us to break up these clusters and build a cluster for a data stream. So that happened in the first half of 2018. We split our clusters based on use cases or data streams, and that helped a great deal from even finger pointing, if you will, right? So if somebody is starving for resources, they will always say, this other data stream is just pegging too much CPU, too much memory, and it's impacting us. So we have kind of addressed that last year. So that was a good thing. Fast forward to Q4 of last year. Wayfair has consciously made a decision to go hybrid. We have a true hybrid system at Wayfair where we have both on-prem data centers as well as data centers in Google Cloud. We use GCP. And we have data centers. We have four data centers in Google and 3 on-premises between US and EMEA. After we went hybrid, we had to deploy Kafka in pretty much every data center because we had data, or we had the Wayfair.com website running pretty much in every data center, right? So whenever there's a website traffic, then you need Kafka there. So we basically more than tripled our node count, even cluster count over the past year after we went into Google. And I'm proud to announce that we have been running Kafka in a hybrid model for the last 4 months without any problems. Seamless interaction between on-premises and the cloud deployed Kafka clusters. As you can see, in Q4 of last year, we expanded to close to 1,200 Kafka nodes, and believe it or not, it's still growing. Fred is the builder on our team, and he keeps adding more and more nodes pretty much on a weekly basis. We also have more than 1,000 MirrorMaker nodes. We are running into a challenge with the number of clusters we are managing, and that's exactly what Fred is going to cover over the next few slides on how all of this is going to be managed like now and also in the future. Right, before you click. Any guesses here on how many messages Wayfair processes these days? The last I think you saw is about 150 messages per second. Any guesses? Either is fine.
100 million.
Little high. 100 million like for a day or for a second? Any other wild guesses? 7 what? Sorry. All right, we can give you the answer. It's about 4.8 million messages per second, or 4.6 rather, which counts up to 400 billion messages per day. So with the numerous nodes that we have, 1,000+ nodes we are processing more than 400 billion messages per day. Just think about it, the monstrosity of this, and it works really well. So that is the amazing thing, right? Yes? What is that? Would you know, Fred?
I don't have that offhand. It took a while to aggregate that.
Yeah, I know.
But that's a great point. We should calculate the data. Yeah.
It varies by cluster and by use case and by topic. On average, I would say usually it's 2 days, sometimes 3 days. But we don't have a lot of like longer except for compacted topics.
Right. Yes.
Are all the nodes same kind of characteristics?
Yes. Some are physical. Our main clusters where we see a huge amount of traffic, they're all physical nodes. We mostly use HP. Now we're going to be using Dell also soon. And the rest are VMs. And we are also deployed in the cloud, so they're all VMs also in the cloud.
That number is including the cloud?
Yes, yes. It includes everything that we have. So it's in the cloud. So it's deployed in the cloud. We use GCP as a infrastructure as a service, right? So it's not a managed service in GCP. So we manage our own clusters, even though they are deployed in GCP. GCP is just like another data center for us. Yes?
Can you briefly talk about the logging infrastructure? What do you use for the logging infrastructure?
Yeah. What is the question?
What do you use?
Elasticsearch. Okay.
For the events, do you use like syslog and
Yeah. rsyslog, Guelph. These are all the protocols we use. Does that answer your question? Yeah. Any other questions, folks? Okay. I'm going to hand over the mic to Fred. He's going to talk about, you heard about how we grew with respect to the number of messages we process and the clusters we manage and all that. Now, Fred is going to talk about the difficult part on how we manage all of this.
How much does it cost to run?
How much does it cost to run it?
More than my salary.
Great question. I unfortunately do not have that metric, but again, we'll probably get back to you guys on that. Yes?
do the number of nodes increase for like on Mayday?
Yes. I'm actually happy. You work for Wayfair? Okay, all right. So we have a holiday, a shopping holiday called Wayday. We started it last year. It's just similar to Prime Day. So anytime it's a Cyber 5, the holiday period or the Wayday, we have to prep for it. Our entire lives revolve around prepping for the Wayday or the holiday, right? So yes, when we are prepping for these holidays, we expand our nodes to make sure we have enough capacity to handle the increased traffic. We see several excess of traffic. I can't reveal how many excess. It's many excess of traffic during these days, and we have to be prepared for that.
But these are like physical nodes, right?
Physical nodes, obviously, we cannot expand. We have over-provisioned. When we bought our physical nodes, we have ensured that there is enough capacity for this year's Wayday, and then we're going to expand more. We are buying another 90 nodes over the next few months in preparation for the holiday this year, right? So, yes. I don't believe we do that. Not yet. Any others before I hand over to Fred? Okay, thank you, folks.
Hi, everyone. I'm Fred Oettinger. I work on Vinay's team. I'm one of the systems engineers, DevOps engineer. And I'm going to talk a little bit today about kind of where we've come in Kafka, how we've gotten there, how our architecture has changed over time, and some of the challenges we face, how we address that, how we monitor our stuff, and then a little bit about the kind of where we're headed and kind of some of the upcoming challenges for us. You can flip it. All right, so this echoes a lot of what Viktor was already showing us, but real high level, I just wanted to show our local-only architecture. So this goes back to what Vinay was talking about when we first started using Kafka in a production sense. We started out, the very first node on that timeline was just when we were testing, and that was really kind of put some things in it, pull some stuff out. And then when we finally got to a production sense, we used local only. And what that means is that we would only have one Kafka cluster, and it would be in each data center, however many data centers we had at the time. And you have your producers producing messages in, you have your consumers pulling data out, and then if you were to kind of abstract and look at the inside of the Kafka cluster, you'd have your topics. And so if it wasn't already covered heavily, it's basically just logical groupings of different types of messages. You can go to the next slide. All right, so when you got further on that timeline, you start seeing our local to aggregate model. And so what that means, and Vinay touched on it a little bit, is basically we decided to start splitting the data across multiple clusters based on the way that it was being used and kind of the interaction that we would have with it. So using a just illustrative model here of 2 data centers, you would basically have your local cluster at the top, meaning that's all data that's produced in that data center, and you have your things producing into it. We would use Mirror Maker, which I don't think was covered real heavily in Viktor's presentation, but it's a tool that allows you to take messages from one place, act as a consumer, produce that message into another cluster, and then it can continue on its way. And so we have down at the bottom these aggregate clusters, and internally we refer to them as C1s and C3s for the most part. But what that allows us to do is we can then mirror the data, and we can split it for a couple reasons, one of which is performance. The use cases for our clusters, the performance is a little bit different between being produced to or consumed from. Think of it this way, if you have one topic and it's being produced into a local cluster, but then on the consumer side, you might have 10 different work streams that are based off of the data that's coming out of that topic. You're gonna have 10 different things all pulling that server, all trying to figure out, hey, what's the next offset, what's the next message? And so what that means is that we've built our aggregate clusters to a different spec than our local clusters. And so, we can have a lot more storage. We can increase the retention time on the topics. Really, just the data here is transient until it gets to the aggregate cluster, and then we can have it retained for a longer period of time. Additionally, you'll notice these red arrows that go kind of across data centers. And so what that does is that gets our data from any data center. And currently, as Vinay mentioned, we have 7 data centers, 4 in GCP, 3 that are on-prem. And it mirrors it into an aggregate cluster at every single site. So what it means is, with a few exceptions for things that aren't needed in other places, we basically mirror all of our data everywhere. And that buys us kind of the second reason of why we do this is so that you have data locality. What that means for a high performance website, when someone goes and they're shopping for a couch, they don't want to go in, click, wait 5 minutes, and then see what the results are on the web page. They want to see something load like immediately, and then they want to see the rest of the pages they're scrolling load very quick. So there's 100 different things that happen when someone's doing a simple browsing operation. And so if, let's say you had data somewhere here in Europe that you needed for that call that user is making on the website, rather than having a round trip time, dealing with the 70 to 100 millisecond latency over to Europe, instead you're pulling it from a local data center. It's sub-millisecond level resolution for the data, times the 100 or 1,000 requests that happen in order to load that web page. It provides actually a very good performance increase. And so that's one of kind of the major reasons that we do mirror most of our data between all the data centers. And then probably the third major reason for that, if you think about it, is for data resiliency. So if data center 2 goes offline, everything right up until the point where it failed is actually already mirrored to the other data center so that you can still have your consumers pulling that data. You may have to repoint a couple things in your workflow, but as a whole, you can sort of operate as if the other data center hadn't gone down. Now, granted, you're not getting new messages that would have come into that data center. And let's say that local data is still working. Let's say it's just a network connection that's severed right here. Data center 2 is still piling up in the local cluster. It's mirroring to its own aggregate. But then once that network connection resumes, we've set our retention periods and sizes such that then that local cluster can then mirror back to the first cluster. And so basically, the data centers can kind of cover for each other and make sure that you minimize the risk of losing your data. Next slide. All right, so on this slide, think of this yellow box as one data center. And inside each of these green boxes, Each of these green boxes are an example of how we've started to separate things out. Vinay mentioned that we've tried to, or rather we've started taking a model of, based on the services that are being run in Kafka and the different topics, we've gone through and started to split things out. And that's for a variety of reasons. Performance is one of the big ones. And I'll cover a couple of the other reasons here in a second. So the first one, general, this is for smaller topics, things with low message rates, low data throughput, and things that, on their own don't really warrant having their own clusters, their own hardware, their own dedicated use case. So these clusters actually tend to be pretty big. We're running, 20 to 30 servers for local and about 40 servers for aggregate physical hardware for these. And so we have, the local to aggregate mirroring across all data centers for the general cluster. Logging. So Vinay mentioned that logging is one of our big use cases. Obviously, every single server, every single application generates lots of syslogs, lots of application logs, and we're using that elk stack that he mentioned. All of those logs need to go somewhere. They need to get into the logging system so that they can be indexed and so that you can go through and actually search for them quickly, especially given Kafka is just a piece of our infrastructure. So those 2,000 servers, we're just there to support everybody else. We're not the main show for the website. And so we have our local to aggregate model. And the use case for that also, the performance that cluster needs is different than, let's say, our general cluster or metrics cluster. You have high volume, but you also have kind of more information. A lot of the logs, especially like in the GEL format where you have a lot of additional data that's included, your message sizes tend to be larger. So moving on to our metrics cluster, as a direct comparison, metrics those are the things that go into our influx clusters, and those are lots and lots of really high volume messages. In one data center alone, we're looking at about 300,000 to 500,000 messages per second just for influx. But those are very, very small messages. It might be a couple characters. It could be a number like the temperature of a server in a data center. So it could be 78 degrees. So it's very small, but it's very high volume. And so we've tailored those servers, the specs that they run, the memory settings, and some of the internal Kafka information. We've set that up to be optimized for that approach. And so that's one of the benefits of starting to split things out is you can really, hey, this is a lot of high volume data. It needs a different amount of storage or a different amount of processing than, let's say, the logging cluster. And then the last set of clusters we have here where we're kind of we haven't gotten to the point where we need local and aggregate, that one set of servers can actually handle the load that these put on, but they're either important enough workflows or they're workflows that do require enough performance that they've sort of justified their own clusters. And so using a couple examples, so compaction, for anyone who's not really familiar, you can either use a deletion-based model for retention of messages or you can use compaction. And so compaction, we've actually separated all of those topics into their own dedicated cluster. And mostly that's for a couple reasons. One is that we don't have nearly as many topics there that need it, but we do need a fair amount of storage in order to let that grow. So over time, as more keys are added, you're slowly going to be taking up more storage and you're not actually lopping off data at the end, other than kind of older values for each of the keys. So that gets its own cluster. Siphon is another example, gray matter, Orwell. These are all kind of internal tools that we've built that facilitate different parts of the business. And so taking all of that together, we've got this yellow box for the data center, and we've got our local data mirrored out and our aggregate data mirrored in. Next slide. And what this really ties us to is this is our model as far as data centers. So each of the black arrows represents a replication stream back and forth and up and down, from on-prem to the cloud and vice versa. So this gives you a sense of, you can have data that's generated in Europe in the cloud and ends up on our West Coast data center, however many milliseconds of latency later. But then you can have that data locality so that you can go and pull information and it will be local to that data center. So you're not doing, transoceanic hops, things like that. Next slide. Oh, yeah. So it's actually the mirror making process. I'm asking only because of the word. Yep, sorry, my mistake. All right, so kind of turning the page a little bit, we obviously have a lot of clusters, a lot of topics, thousands of topics, thousands of servers. And managing this, we're actually a pretty small team. We've got 8 people on our team right now. And so that's managing the entire infrastructure, both GCP as well as on-prem. So a couple of the ways that we approach that, one is that every single day we have a dashboard that someone generates and then puts into email and sends to the team before 11 o'clock in the morning. And we go through service by service, and I apologize, there's some things blacked out here, but basically service by service, you would go down, investigate the service, figure out what the current status is. You would include some notes, and that's sent out to the team so that when everyone's in the morning, kind of after our daily stand-ups, you have a sense of exactly what's going on with the clusters. One kind of important thing to note is the person who's on this rotation, so we have an operational rotation on our team, and so every week it shifts to a different person, is that they are not there to troubleshoot. They're there to identify what's happening, provide a status update, and send that out. The troubleshooting either happens from other members of the team or it happens after that initial kind of analysis of what's happening. Where that's important, especially you might think, okay, hey, wait, what if a server's down? What if there's like a more serious issue rather than in this case, there was under-replicated partitions in one of our clusters or one of our data centers. And if a real serious issue is found, obviously that person's going to flag whoever the on-call person is, or they're going to ping the engineer next to them and say, hey, I got to continue with the daily checks, but here I need you to take a look at this right away. So obviously that's used with some judgment and kind of a how serious is this, but this is something that we've actually found to be really helpful. And you'll see on some of the upcoming slides how we've managed to get a global view of all of our systems pretty quickly. The second, as Vinay mentioned, is our Cyber 5 and Way Day. So Cyber 5 is the period of time for us where it's between Black Friday and probably a couple days after Cyber Monday. That's our heaviest site traffic. There's all the promotions and marketing and get couches at a discount, that kind of stuff. And so we see huge website traffic. And then Way Day is 6 months around the calendar year. So basically every 6 months we have a major kind of sales time. And so those are really kind of our focus is to prepare for those. And so on Cyber 5 and on Way Day, we've generated and built a whole series of kind of high-level dashboards and procedures for quickly ascertaining what the status is of our systems. And so we have those kind of at the ready. And so anytime there's a problem, or whether a real problem or an example is that we run frequent kind of fake system outages. We had one today, actually, where they just spontaneously message the team. They say, hey, we're having a SEV. Everyone drops everything they're doing, and they run through whatever parts of the procedure that they've been assigned. And within 7 minutes or less, I think, 7 minutes or less, we can get an overall status of everything that we have. We can pinpoint where there are problems. And it's kind of interesting, actually, when we're doing these, even if there's not a real issue, like let's say it was simulated like today, usually someone will say, hey, processing's looking a little hot in this data center, or hey, this cluster has a node that's having some problems. So it allows us to pretty quickly identify problems. And with a team of only 8 people, that's absolutely paramount. So on the next couple slides, I'm going to cover kind of how we do that at a high level. Next slide. So obviously, the first piece of that is you got to have to know what you're looking for. And there's a million different metrics. There's all sorts of stuff you can get from Kafka. But we've had to distill that down into a couple KPIs. For anyone who's not familiar, KPIs, key performance indicators, pretty standard terminology. And so the 4 that we've kind of arrived at for our brokers are under-replicated partitions, or ERPs as we call them, offline partitions, disk usage, and message rates. And what we've really found is that these are the best representations of a truly important system outage, a truly important system outage, and are something that needs to be acted on if we have problems. Disk is obviously something that, since we're processing our log streams, if somebody all of a sudden their systems go haywire, or somebody pushes bad code that affects 100 servers, your message rates might triple, they might quadruple, and that has a very real consequence in Kafka. Now, granted, we set retention limits based on time and size, but just using that as an example, that's something that, hey, if a broker fills up, instantly the services stop on it. So that's something we need to keep a close eye on. And then next slide, or next button. So mirror makers are the same thing. Obviously, since we rely on this mirrored architecture, one of the most important parts of that is making sure that that's operating. Is anyone here familiar with Mirror Maker? Have you used it before? All right, one person. So Mirror Maker, it's kind of known for being really good at what it does, but then it doesn't handle problems very well. And so one of the things that we always need to check is the process running. And it sounds obvious, but it's one of those things that if Mirror Maker encounters an issue, so let's say you're sending a topic through it and it doesn't find the topic on the destination. Let's say you just created some topics in 2 data centers and maybe there was a problem or a typo in the name on the second data center. Mirror Maker will literally just stop. The processes will die and it will just sit there. So we watch our mirror maker processes. Bytes in, bytes out, we look very closely for any kind of spike in the network traffic, up or down. Up generally means that somebody else is having a problem. So it's not good, but it's something that we keep an eye on. We notify, hey, which topic is it? We can go through in our dashboards and generally notify those teams, hey, it looks like you're having a problem. Hopefully they've heard about it before we tell them. Memory usage, so mirror makers, they don't really have any onboard storage. We don't really care what's on them. They're not important servers. We don't rely on any single one. And the way that we scale our clusters, we can add nodes, we can tear nodes out. The one caveat to that is that mirror makers rebalance every time there's a change to the number of nodes in the cluster. They basically find quorum among whatever nodes are online. And so there is a little bit of a rebuild process as they kind of figure out who should be replicating which partitions. As such, they're not storing anything to disk. It's all in memory. Data comes in, stored in memory, produced out to the next thing. And so memory usage, we should see it be pretty flat across the line. Mirror maker only takes a certain amount of memory. If you see that spiking or dropping, it's generally a problem. And then load average, obviously if it's just processing data through, you want to keep an eye on your CPUs, make sure they're not running too hot. So those for mirror maker, those are kind of the real critical KPIs. So anyone who's running Kafka, if you're going to use either brokers for Kafka, but mirror makers, those are some of the things you should probably be looking at. Next slide. Yes?
Which one of those is actually actionable? Start, polling people and people start running around.
So the question was, which one of these are actionable, or kind of how do we approach these? For us, pretty much all of these are actionable within certain thresholds. So, message rates, if we see a spike in message rates, generally it's not a problem. It could be that marketing sent out an email at 11 o'clock and all of a sudden there's more user traffic, which means there's increased logs, there's increased metrics, there's all of our thousands of other topics. But if we saw message rates either drop precipitously or, wow, there's 10 times as many messages as a second ago, generally that would be, we've set a threshold for that in our alerting systems. But also, at an eye level, human level, you can start watching trends. And if you see any kind of a line where it's a very steep, nearly vertical one way or the other, that can be a sign of a problem. And all of these are like that. The bytes in, bytes out, I would say is a little bit less so, only for the fact that there are so many different things routing through our clusters that it is difficult to discern, hey, this big network spike is tied to this one specific thing. And so part of us in splitting our clusters out, part of that has been to help isolate and separate traffic flows, so it's a little bit easier to wade through those. The clusters that we have separated out tend to have very high network traffic. Does that answer your question?
Yeah. Do you do any tracing and in each type of tracing you see message, what kind of message or what causes the problem, so you can pinpoint the components? More like a knowledge, not the message which is kind of, whatever message, but actual subsystem that caused the problem. Like, do any analysis on message level, trace back to the source?
Not directly at the message level, but among there's additional metrics that we look at. We've built a number of different dashboards. We can look at the topic level and we can obviously go in and tail one of the logs and see the data coming through. It's something that we're starting to look at, but it's not something that we're doing actively yet, or it's not in production, I should say. Any other questions before I move on? Yeah.
So I heard you guys talk about the number of message processes from those. Do you also have a number of topics actually, and are there any guidelines on how fine-grained the topic should be?
When you say fine-grained, what do you mean?
The topic can be grouped and then the consumer can go for a particular message and skip if it's not belongs to the particular consumer and then move on to the next.
So I think what your question, and just correct me if I'm wrong, is you want to know if we've separated our topics out based on the type of use case. And so for the clusters where we have separated them out, we have. And then I think a tangent to your question is figuring out how much one broker can handle, because you want to know how many messages or how many topics should I put in one cluster versus when do you determine that you need something bigger? The answer is sort of. Excuse me. So for each of those cases where we split something out, it's when we've started to see either failure domain. So one set of topics started to fill up a cluster and it was impacting other critical things, or wow, if we go and look, 99% of the traffic or 95% of the traffic is this subset of 5 or 6 topics, such as the scribe data that Vinay mentioned. When you start seeing that individual pieces or groups of topics are kind of monopolizing the resources, that's when we've started to have those discussions. In 1 or 2 cases on the previous slide where I had a few of the ones that weren't quite local aggregate, but they were special use cases, we've had a user or a team approach us and say, hey, we want to do this new thing. Here's our anticipated message data or some of our requirements. And we've started to realize as we talk to them that their use case outside of what we've spec'd for. And so then usually it starts to be a discussion of justifying business use case and figuring out what kind of budget are we looking at. In a lot of those cases too, I should add, not all of our clusters are huge. We have clusters with 4 or 5 nodes and that are running on VMs and are pretty small in size. And so that allows us some better flexibility than buying a $50,000 server or 5 $50,000 servers that are real powerhouses with half a terabyte of memory. Instead, you can run some VMs that are 8 cores and 32 gigs of memory or something and a couple terabytes of storage. And so it's really on a use case basis. But in general, like when we start to see things that might concern us, and especially where uptime is the most important thing on the website, that's helped us make those choices. Yes?
Addendum to that question, how many topics across Wayfair do you have to follow?
Sure. So I would guess in the neighborhood across all clusters somewhere around 10,000. I don't know for sure. I'm thinking of, we have a couple real big clusters that are in the 1.5 to 2.5 thousand topics. And it's just given the sheer number of clusters. Now, when I showed the C1s and C3s and that square box of data center, there are a lot more clusters than those. Those are just the ones that are kind of the biggest kind of categories. But we have a fair number of additional clusters. So that would be my guess, somewhere in that range.
And how do your consumers find topics that they should subscribe to when you have so many catalog or some kind of way?
So we do provide Kafka Manager to everybody so that they can go in and look. And if you're not familiar with it, it's just a simple UI. It's got an API so you can query against it. But it has every single cluster in it. You can click on a cluster and see a list of all the topics. You can see the message rates and that kind of thing. But to answer your question, that's not actually how people figure out what topics. Usually they come to us and they say, hey, we want to do a workflow in Kafka, and we build a topic for them specifically. There are some cases where a team will be like, hey, we heard such and such teams using like inventory updates in a certain topic. Can we piggyback off of that and consume from it? And as long as we're not making changes to the original owner's topic, they're just a consumer, we have no problems with that. Yeah?
You guys go down publishing contract for
I'm sorry, what do you mean?
So the structure of the message,
Mm-hmm.
do you have any central location that you publish, okay, this is the structure that we expect in certain.
So we don't, for the most part, I should say, we don't, I was gonna say we have schema registry, but there are also a lot of times we don't dictate, at some level we don't dictate what's in the topics, but for things where obviously people are expecting a certain format, then we use it. Does that make sense? All right, next slide. Thank you. Oh, sure. So just high level, so those are our KPIs. So this is one of the dashboards we use for our brokers. It's separated by data center. So we've got 3 of our on-prems, and then this is actually a section of our cloud presence. Under replicated partitions, offline partitions, disk usage sorted by highest and then descending, and then our message rates, and generally looking, I'm sorry?
The answer to that last question is
18,000. So that's about double what I thought. And that's the thing is we get so many topic requests, which I'll cover here in a second, that we really have to, there are a number of ways we approach that. So anyway, we look for outliers here. You can see we've got one host here that's showing an under-replicated partition. And that allows us at a glance to look at thousands of servers and then quickly identify when there's a problem. Next slide. So same thing for our mirror makers, little different format, but same thing. We've taken our KPIs, we've separated out by data center, and without explaining how every single thing is interpreted, we basically, we can look for spikes, we can look for changes, we can look for things that are highlighted in orange. And this allows us to at a glance look at whatever the thresholds, bless you, whatever the thresholds that we've defined, and allows us to kind of quickly pinpoint where there's a problem. Next slide. All right, so looking forward, a couple of the big, I think, did it miss a slide? All right, actually, there it is. I edited it today, so I didn't remember. So automation is one of our biggest things. And to answer your question about all the different topics, so one of the biggest things with a team of only 8 people and obviously 18,000 topics, we get a lot of requests. We get a lot of requests to change things. And so scripting out topic creation, setting a set of guidelines, dumping it into a script, and then letting that script validate if this meets our needs or not. Vinay actually wrote for us one of the tools that we're using right now that's just gone into production. And that's taking a couple day turnaround time for topics and making it now our SLO, our target objective, is less than 8 hours. And additionally, just kind of a lot of the different pieces of administration for Kafka we're working on automating. We've got a couple tools built in-house, as well as we're using open source things to help streamline and speed that up so it's a little easier for us. One of the other things we're looking forward to is we're in the process of starting to POC replacements for Mirror Maker. Obviously, if your tools that are mirroring are the same size as far as node count as the actual things that you care about, that's a bit of a problem. It gets to be very difficult to manage. And then there are a couple downsides to Mirror Maker, one of which I mentioned, where it's not the most stable thing if it gets anything other than exactly what it expects. So we're in the process of looking to kind of condense and streamline that. That should end up helping us cut down on node count and making administration and management easier. And then the last thing, Viktor obviously had mentioned some of the differences between a traditional messaging system and Kafka. We have Rabbit. We're looking to replace most of the workflows we use for Rabbit with Kafka. A lot of times there's no real reason that someone put it in Rabbit other than Rabbit was the tool that was available. Now that we're using Kafka, most of our workflows are going to be pulled out of that and put into Kafka. So we're working with different engineering teams, kind of cut down the number of tools we have, and there will only be a subset of things that end up in Rabbit. Next slide. Oh. So there are a couple of things Rabbit's really good at. I'm not a Rabbit expert, but one of the things that I remember talking about with some other engineers is that Rabbit is really good at taking a huge volume of data. You can apply a filter to it and getting just that stream that you care about coming out. So an example that we could use would be when a user goes to the website and they have a unique user ID, we can go through, take the whole stream of all the web server logs and database calls and all that stuff, filter it by that user ID and see only their stream of things. So when you're going through and trying to figure out, why is some piece of the website not working, when a user does this exact specific thing, we can actually use Rabbit to go and funnel that rate down. Rabbit's really good at throwing things away. And so that's not something Kafka does. Kafka doesn't do the processing. That's dependent on the consumer code. So that's an example of why we would use Rabbit. Well, we're not using KSQL yet, but that's something that we're talking about.
The rest of the Rabbits.
Yeah, so we're not using it yet.
Actually, it's like a bread and butter use case. Like out of the box. It's like don't need to do anything else.
We've got several people who've been kind of prodding us for KSQL, and so that's actually something on our roadmap to start investigating and POCing and testing. Yep. So for kind of that side of it, we use kind of the in-house tools built into Kafka. We're in the process, so we have KCC, which is Kafka Cruise Control, which actually does a lot of the rebalancing and kind of shuffles the partitions around. It allows you to evict a node from the cluster and automatically do kind of all of the necessary work to do that. That's one of the things that we're working to automate every single piece of those painful rolling restarts as much as we can. So we're working on that, but it tends to be a challenging thing to do. And there are a couple ways out there on the internet that you can do it, obviously using like Confluent Enterprise. So there are different ways you can approach it, but we're starting to use some of that stuff.
There's also LinkedIn's got a couple tools out there. I think it's like Kafka tools or something like that.
Pinterest. Either Pinterest have some set of scripts like Kafka tools.
Yeah. So there's a couple things out there on GitHub.
If you Google like Kafka tools Python, you'll get a rolling start. Datadog is actually they released something that doesn't anything, any tools. They just kind of reverse engineer the protocol for the people. They use their own tools like partition reassignment and everything.
That came out just recently, I think, too.
They spoke about this on Meetup, and they actually have a blog post. I really like it. Yeah.
Next slide. I think that's it. So I don't have a business card. I don't know if Vinay does, but I wanted to include all of our contact info so that anyone here, feel free to take a picture, and you're welcome to reach out. We're looking to be a part of the Boston Kafka community, and kind of hear how you guys are using it, answer questions, probably ask some of our own, hear about different use cases. We're obviously using it for very specific things, so I'd be curious some of the other ways that you guys are using it. And then one last slide. Does anybody have any questions for any of us? Thank you. Yeah.
Yes.
Do a structured performance test in any way, or decide on the hardware, or
I mean, generally, honestly, our hardware profile has been overkill for what we found. The limit tends to be how much disk space we have rather than any of the CPU memory. We've got 10 gig networking everywhere in our data center, so we generally, I mean, we deny it, but we generally don't hit any of the, we don't hit any physical limits on our.
The company as a whole does these pinch tests from time to time, like every few weeks. So that is when they simulate huge amounts of traffic, which in itself will exercise all our systems. So that is our test. I've been here for 9 months at this company. Not a single time people pointed a finger at us so far. Knock on wood. With all their pinch tests, and it's somebody else most of the time. So distributed systems is cool that way.
Any other questions? Oh, you and then go for it. You mean live on the website? So we use it for things that Vinay mentioned, like the recommendation services, that if you're looking at something and then you click on the next page, your results are probably going to be different based on what you've done on the previous page. And then Kafka also supports a lot of the kind of back-end stuff that's not necessarily visible to the user, but it's the metrics and tracking about the user, the things that are in the cart, some of those pieces.
Ad serving is another great example. So we need to make split-second decisions what type of ad we need to serve. So if you go to Wayfair.com and then you browse to Facebook or something else, you'll still see a little pop-up or a little ad somewhere on the side, right? So that happens, again, using some of our technology where we decide if this user is worth enough that we can serve an ad. We call that customer scoring.
Oh.
Do you manage access to a full top?
Not yet. We're working on that. Right now, we're pretty much in a wide open.
What kind of mediators?
Yeah. We do control like topic creation. It's not that much of a free for all, but we haven't implemented anything else yet. But we're looking at that as we're getting some more people interested in Kafka who are dealing with more sensitive data. Like I had the Steam project as that if they start enriching those data streams with more sources of data, they're definitely not going to want anyone in the company to be able to do like stream of credit card transactions. We don't none of this is exposed externally. It's all within our data.
All internal.
no SASO headings?
Not yet. No,
We're all behind firewall.
We actually have a big prize all the things that are going on, and that is going to be
Tom is living in that world right now. By the way, he's a senior engineer on our team also.
All right, so before, one second here, before we leave people here, lose people, just want to get some feedback on the session. So how often you think, Bashu,
Hold on. This one's blank. Sandeep from, oh yeah, nice. Very good.